I'm Matthew Avaylon. I am a core developer on the NWB team. I'm a main maintainer on HTML and HTML czar. And so I'm going to talk to you about backends that we have and some events data IO tools that we have. So sorry, let me just kind of get situated here. There we go. So once you really start dealing with data sets larger than a few gigabytes, you might want to start looking into how you store this data efficiently. And what efficient means will depend on how you'll be interacting with the data, how you think others will interact with the data. I won't go too deep into these topics, but I want you to be aware of what is possible. If your data writing is too slow, your analysis is too slow, file is too big, or your computer does not have enough RAM, you'll remember this talk and you'll go to the right tutorials on the website. All right. So let's first talk about the support of backends. I do believe Oliver touched on this in day one, introducing NWB. NWB uses HDF5 as its main storage backend, and a few reasons for that being it supports large-scale data storage of complex data in a single file, optimized performance. So today we'll be talking about chunking and compression, and really it has targeted long-term support. Now, I believe 2022, but it really picked up steam in 2023. We introduced czar as a backend through HTML czar, and this is mainly for people who want to do operations analysis in the cloud. And we also support chunking and compression with czar. So I just wanted to kind of plug this just a little bit, but it is related. So we have over 250 NWB Dandy sets, whether it's Micron's 2-photon functional imaging or Allen Institute OpenScope. And this would be a blend of whether it's using HDF5 or czar. I did talk with Ryan, who is not here today. There is czar files on Dandy, but you cannot publish them. So you cannot get a DOI, but they are there. But the vast majority are using HDF5. You can see Mouse and Rat kind of being the most popular. EC of his really kind of takes the cake there. But yeah, use this QR code. Check out the NWB data sets that we have on the Dandy portal. Leave that up there for, all right, let's go. So one thing I really want to stress is that no matter what backend you use, the user workflow really doesn't change. So this would be y'all having your experimental data. And NWB supports a wide array of neurophysiology data types, from electrical and optical physiology. We had tutorials and talks about that yesterday, to behavior experiments. So you would take your data, you would instantiate and populate your NWB data objects, and then you would add those objects into the NWB file itself, and then you would write it. And then ideally, you would upload it to Dandy. But just a quick plug here. When you have large data sets, specifically, if you're looking at other people's work, having context really is helpful. And so we have herd here as well. And your backend doesn't actually affect how herd is integrated into your workflow. But we'll talk more about herd, contextual metadata, validation shortly. I'm gonna click. Okay. So this is mostly just to stress the fact that writing using either the NWB HT5 IO or the NWB czar IO, they're very much the same. All right. Now we have those two backends. You're not locked in to either one of them. So let's say you have an HDF5 ready yet. You find a file on Dandy that is HDF5. And you want to convert it to czar because you've embraced the cloud. You can use export, and export you will convert and or modify an existing NWB file. But what's really important to know is that it doesn't replace the prior file. It preserves it. Export, it has a lot of stuff going on in there, and so I highly recommend checking out the tutorial. I'll be around as well. If you guys have any more questions kind of throughout the hackathon user days. And I stick around for, not stick around, but stay tuned for release on Zar in the next month or so. It's kind of an expansion on export on the Zar backend. All right, so kind of transitioning more towards the advanced data I/O tools. We have multiple ways of making reading and writing of large data sets more efficient. First would be modular data storage. This is useful if you want to store your data or process data across multiple files. For example, if you have multiple recordings, different recording sessions, or even different electrodes on the same session, you can write them to different files and have a main or master file that links to those other files. Second would be chunking and compression. We'll talk about this very soon. And this is useful if you want to really optimize your data storage for particular ways in which you want to access the data. So say you have a time series of electrical recordings from a neuron, and you present the animal or neuron with a stimulus of 1,000 times, so 1,000 trials. And you really say you're only interested in the 5 seconds before and the 5 seconds after the stimulus onset, then you can organize your data in such a way to really prioritize that 10-second long pocket data. And then finally, we have iterative data write. This is useful if your data is too big to fit into RAM and you need to write or read chunks one at a time. Now, I'm only going to be talking about these two here, but again, here is a QR code. After this talk, I can leave this up for anyone to scan to really get a deep dive into not only these topics, but this QR code will take you to other advanced I/O tools, and I think just in general to our tutorials page. So kind of you guys can take a deep dive there. All right, chunking and compression. So let's get some context here. Data arrays are stored contiguously. So this means that on disk, in memory, the elements of a multidimensional array are stored in a one-dimensional buffer. And so let's say you had a table that you would see it has more values for quick access for a row, then you would think about having a read pattern that follows this. Same with the idea with columns. Now, sometimes there is no row or column bias, and you kind of just want to have a compromise. You can set the shape for chunks as well. But we can see this in NWB. So first off, just create a NWB file per usual, and then we would import H5 data IO. H5 data IO is a wrapper that enables chunking and IO filters, and we can use it to wrap our data and set the chunk and shape parameters. So here we have, a toy data example, and then we wrap it with H5 data IO. We set chunks to be true, so this will enable chunking. And with max shape, set to be none. This will make the time dimension unlimited. It can be resizable. And this wrapped data itself would be the data in your time series. Say this is actually raw data, so you would add it to acquisition, and then you would write data per usual. Compressing is very much, I'm not going to be the same, but it's similar in that it also uses H5 data IO. So you have your NWB file, you have your toy data in this case, and then you can use gzip, and you have your compression options as well. This wrapped data is the data for the time series. You can add it to acquisitions. H5Py, supports really a number of different compression algorithms, gzip, szip, or LZF. However, only gzip is built by default into HDF5, and this is all lossless as well. All right. So I mentioned prior that you can also compress and chunk data in Zar. In this case, we actually have a specific shape in mind, and the compressor that we're using is BLOSK. Caution, fair warning. Chunking and IO filters can help reduce storage and IO costs, but it also can harm performance. So don't make chunks too tiny. And really, if you have no real idea of what size it should be, then I would just follow suit on, where is it? This one, where chunks is true. And H5Py will kind of set a default shape for you, and that is usually pretty good. So I would start there. All right, iterative data write. So what is it? In the typical write process, data sets are created and written as a whole. In contrast, iterative data write refers to the writing of the contents in an iterative fashion. So one chunk at a time. So use case you can think of it. So you have large data arrays. A central challenge when dealing with large data arrays is usually you won't have enough memory to load it all at once. And so using an iterative data write process allows us to avoid this problem. You write it at one subblock at a time. And so that one subset is the only thing that you have in memory at any given time. Data generation or data streaming. There's several issues that kind of come along with this, but one to highlight would be that the data is not available in memory because it arrives in subblocks through the stream itself. Right. So more context here. So in PyNWB, the process of iterating over a large data array is implemented through a concept of a data chunk and an abstract data chunk iterator. A data chunk is a data structure that is used to describe a subset of a large data array, a chunk of data, if you will. And the abstract data chunk iterator is the base class for iterating over large data arrays, one data chunk at a time. This is the base class for all iterators. So you would use this as your parent class to create your own. We have the data chunk iterator here. And this would be an example of using the abstract one. And it iterates over the first dimension of an array, which may not be the best method for you. So feel free to embrace creating your own. All right, some examples here. All right, so here we have a simple data generator. And PyNWB makes no assumption about what happens inside of this generator. So instead of creating data programmatically, you receive it from an acquisition system or a stream. And so you take the generator itself, that would be the data inside of data chunk iterator. And that's it. And after that, you just write it per usual. So you would have your NWB file, you have your time series. That data here is the data chunk iterator with your generator inside. Let's say it's raw, so you added two acquisitions, and then you would write your data per usual. Our last example here. So when converting large data files, the last one is we have data coming in, it's fresh, it's new. And now we have, let's say, a file that we want to read from and write into NWB. So in this example, we have a generator that will read a NumPy file in chunks, and that will yield it to you in batches. And so the same idea, you have this generator, it'll go into the data chunk iterator for data, and then you would write data per usual. So NWB file, your data chunk iterator data, write to disk. And that is it